Okay, thanks very much, Sidi. And thanks to the organizers, Peter and Kunle, for this really fantastic meeting. I'm really enjoying being here. Okay, so what I want to talk to you about today is some work that we're doing. And so my title is 3D Spin Textures for Reconfigurable Magnonics in Neuromorphic Computing. Actually, since I wrote my abstract, I've changed what I'm going to talk about a little bit, and I'm going to really focus on the Magnonics rather than the Neuromorphics, but I'm going to at least motivate the work that we're doing within a framework of the things we've been doing in the neuromorphic computing. Okay, and so you're listening to me. Obviously, this is a massive team effort, and so you can see the author list here. So this is really a joint venture between Imperial, UCL, Delaware, Colorado Springs, and Kyushu. And like Benjamin is actually talking next, so he's obviously part of that team. And I guess the most important thing to say is that really the two most important people in this talk are firstly Troy Dion, who has worked with me for quite a while, but he's now a fellow in Japan. And he's done basically all of the simulations that I'm going to show. And Jack Gartside, who is currently a Royal Academy of Engineering fellow, and again is becoming increasingly independent of me. And like this project, really, he is the lead. And so I'm one of the co-authors, but this is really his thing, and maybe he should be giving it rather than me. But I'm delighted to be invited, so thank you. Right, okay, and also just to say quickly, so basically most of the stuff I'm going to be showing you is published, and there's a lot more details, or in fact not published yet, but it's about to be published in Nature Communications, and so there's the paper there. Right, okay, so what are we trying to do here? So really, Laura gave a fantastic introduction to artificial spin ice, and I've worked on that for many years. And so really, what I want to look at is what can we gain, or what's going to be different if we kind of take it into 3D, or if you prefer 2.5D, where we make a sort of really entry-level 3D structure where we just put a couple of these layers of artificial spin ice on top of each other with a spacer in the middle. And so really, well, what we want to do, I mean, there are many obvious benefits to going to 3D in terms of the computational power you can get, the density, the volume of material, also just the complexity of the thing. So Giovanni showed that complexity can be very important for the sort of computations that we want to do. Right, okay, so, and then basically we want to explore, even in this really, really simple 3D array with just like a very simple ferromagnet, which is just going to be permalloy, and then just a spacer layer to allow the dipolar coupling through the stack. What I'm going to show you is that this enables a really massive enhancement of both the sort of static dipolar coupling and also the dynamic dipolar coupling within the system. And that's going to reveal, even in these really simple structures, some really exotic physics that goes on. And really that promises, a new generation of these artificial spin ices with improved properties for the computation. Okay, so this is the framework. This is, if you like, my personal motivation for why I'm interested in these things. I'm going to rely on Andrew to motivate the kind of basics of Magnonics in the tutorial later today. But so basically, this is the kind of scheme by which we are doing neuromorphic computing in these systems. And so very soon after people started making artificial spin ices, one thing that they discovered is that actually these are really good reconfigurable magnonic crystals. And so really what that means is like the exact magnetic microstate of your array controls very precisely the ferromagnetic resonance spectrum. And so we have been able to exploit that. And so really there's a few papers, with my pointer down here. So, sorry, I'm not plugged in, right? Okay. Here we are, yes, I'm too quick, okay. So in this paper by Alex Vanstone here, what Alex really showed was that the FMR spectrum that you measure, it's not just like on some level controlling or changing the ferromagnetic resonance, but really the ferromagnetic measurement is like a proxy for really quite detailed information on the exact magnetic structure that you have. You don't have the spatial information, but if you think about the sort of vertices that Laura showed, then you really can see the kind of vertex population. So you can not only see like what state your bar is in, but really what the neighbors are doing. And so then what Killian Sterning and Jack Gartside realized, and we showed in this paper here, is that what that means is that this is like a really powerful readout for a computation, which is essentially based on the updating of the magnetic states. So many of the neuromorphic things that Giovanni showed are like trying to exactly mimic what is happening in a kind of software neural network in the hardware. And this is not like that at all. It is a form of reservoir computing we're going to do. And in this reservoir computing, basically, we are going to have some input signal. And the first thing we're going to do is we're going to scale that input signal or renormalize it so that all of the inputs we might apply, our system is going to care about in some way, but then none of them totally wipe all the history in the system, because what we need our reservoir to have is what's called a fading or echo state memory. And so really that means that it cares not only about the input that is happening right now, but also it cares about at least some preceding inputs, but you haven't perfectly memorized all of your training data. Okay, so as long as we do that, so here you can see the range we've scaled it to about 18 to 23 milliseconds from this particular case. And then we cycle minor loops and we update the magnetic state. Then that updates our fMR spectrum. And then we do traditional machine learning, but of the most simple sort, a simple linear regression on the output. So we only train the outputs, which in our case is essentially the intensity that we measure at each frequency in our spectrum. Okay, and actually, this strategy is hugely transferable to other systems. And so here we have very nice Nature Materials that came out this year, working with Hide Kurabayashi's group, where we basically took all the stuff we developed in artificial spin ice and we did it in a bulk skyrmion crystal film. And there we see excellent computing performance there as well. And so that's obviously a very different system, but in that system as well, it worked very well. So this is a strategy that is probably applicable on some level to many of the systems that the people in this room are doing. And so we'll be very happy to talk to you if you want to think about it in your particular system. Right, okay, oh, sorry, one thing I didn't say. So actually, this is really, really good and very, very potentially applicable with one caveat. At the moment, we are using global field as our input, and that is really slow. So that's not good at all. And so we do want a kind of collective input. So we don't just want to necessarily only control one bar on its own, but we do need to go fast if we want to be credible as computing. So how are we going to do that? So really, our computation is relying, at least in the artificial spin ice case, on updating the magnetic states. And obviously, there is loads of credible, already technological ways to quickly update magnetic states. So there's lots of ways you could go. If we could do that already in the setup, we would have done it already. So obviously, there's development to be done there, but there's lots and lots of ways that you could imagine doing it. So anything that's similar to an MRAM or all optical magnetic switching or a racetrack device, these are all things that you could think about doing. And while these are hard, they're certainly doable. But the thing about going to 3D is that in most cases, that is going to be even harder, either getting optical access everywhere or wiring everything up. So maybe that's not at least step one for us. But also, you could say, well, Will, you're already made a magnetic crystal, and you're already measuring the fMR, so why don't you actually try and do some proper magnonics and try and input and compute with the microwaves? And so that's what we're going to think about now. And so really, our interest in 3D was first piqued with this lovely paper by Gianluca and Kunle and friends, where basically they showed just by making nanowires in this kind of tri-layer stack, you break symmetry in a way that gives you non-reciprocity in the dispersion. So that's one way that we could get the sort of non-linearities in the magnonics that we would need to do some sort of computation. And we know that if you bring them really close and you make a SAF where you've got exchange coupling, then, so actually this is somewhat different to our system because of the exchange coupling and it's so strong. But in your SAF, so here you have two modes in the magnonics that are orthogonal to each other. So you can see that they just cross without any interaction or hybridization. But then if you break the symmetry with a global field such that these two modes, acoustic and optical modes are no longer orthogonal to each other, you can see some sort of hybridization starts to come in, and then as you increase the field, and so you break the symmetry more and more, you can see this gets really strong. So this is like gigahertz scale hybridization coming in here now. So, and this is work from Hide Kobayashi's group. Right, okay, so it's definitely attractive. So we really like the reconfigurability. So going to a SAF is probably too much for us because then, the exchange is so strong you can only have the alternating state. So, but what we want to do is something similar. Sorry. And so here we're going to have this system, and so now we're going to have islands, so basically exactly like Laura showed. And so basically by going into the third dimension, so we're going to have dipolar coupling, and the first thing to say is that, at least at the spaces we're at here, this coupling is much stronger than the other couplings. So we're not doing fair artificial spin ice with all couplings being exactly equal anymore, but instead, we do have like a hierarchy of interactions, and this one is the strongest. Okay, and so we get nice, strong coupling, and so basically for strong nonlinearities in the Magnonics, we want strong dipolar coupling. But then, as well as in, if you like, the static dipolar field, so lining up very nicely, or not, so what I want to say. So this, so here the stray field coming out of this bar wraps around nicely, and then it lines up with the internal field of this bar. So that will have one sense of effect in the FMR measurement, whereas here the stray field coming out of this bar is going to be anti-aligned with the internal field of the other bar. So they cancel out, and you get strongly different responses. And so really the thing that is most attractive to us about going to this 3D structure is that very often, if you look at the spatial distribution of where your Magnon modes are, for example, here, this is a heat map of the Magnon power, and you can see it in this particular mode, when this is kind of typical of like the strong modes that you get, you can see that the action is really localized in the center of the bar. So you can see that when we stack them up vertically, we can get the, where the Magnon action is really close. So in our case, like about 30 nanometers apart, whereas this lateral separation, it's hard for us to get less than like 500 nanometers or so. So in terms of the dipolar dynamics, we can really make a massive difference to how close we can go. Okay, so Laura's introduced really nicely all of the basics of artificial spin ice, so I won't dwell on this, except to say that you can make really anything you like. And the thing that we want is basically to access as many as possible of these 2 to the n states, and also for them to be metastable, at least. So they don't all have exactly the same energy, but we have this huge manifold of states that are all accessible and metastable. So maybe you put a field on to get them, but then if you take the field off, they will stay. And so when we do things like that, we can start looking at how the Magnonic control goes. And so as Laura said, in a lot of standard artificial spin ice structures, you have this huge number of possible states, but it's actually really hard to access very many of them. And so the first trick that we developed is something we call width modification. And basically what that means is we have some thin bars and some fat bars, and they have slightly different coercive fields to each other. And as long as that difference is more than your kind of natural variation from the quench disorder in your fabrication, then you can set the thin bars and the fat bars separately with fields, and so you can access many more states. And so here we have our classic spin ice type 1, type 2, type 3, and type 4 structures here. And these are MFM pictures, and you can see that we can really make the periodic ordered structures of all of these. And then when we do, we can look at the Magnon spectra. So here are vertical slices of frequency as we change the field. And at least in the field windows where we don't wipe the history, you can see the evolution of the different Magnon modes. So here's the type 2, the classic one, where they're all magnetized. And you can basically see that all the modes here, they kind of have the same Kittel response. And so they just stay parallel to each other, and there's no coupling. And actually, the reason that it was hard to see these sort of Magnon coupling effects in artificial spin ice was just you couldn't get the right state to see it. But as soon as you can access a state where some of your bars are with the field, and so they go up in frequency as you add more field, and some are against the field, so they go down in frequency. Sorry, I'm not very good with this thing. Then you can get a crossing. And so then if there's a crossing, then you've got a chance of seeing the sort of hybridization that we want. Okay, so do we see hybridization? And so the first thing you can say is that in this 2D structure is that it's weak. It's kind of like the separation is close to the line width, but I hope I can convince you that we can just about see in the data here that we do have an anti-crossing. There is a little gap. And so this is all described in this Nature Comms paper from 2021. And so what's going on here? So if you like, the dashed lines are the bulk modes of the thin bars and the fat bars, but then which are magnetized in opposite directions. But then, when they cross, then at least where it's curved, you get a hybrid mode, which has the character of both. Okay, so that takes us to 3D. And essentially what we want to do is make these coupling effects much stronger. And also it would be nice for us to have more complexity as well, or just more modes, more states. And so we've actually added another ingredient here. So basically we have made our top and bottom layers at a specific geometry where the nanomagnet is very close to the crossover between just wanting to be a uniaxial dipole or a macrospin and a vortex, so that both of these things are metastable. So each bar can have 4 states rather than 2. And then, just because we've got 2 bars, that gives us a total of 16 possible states per unit. So rather than having just 2 possibilities, we've now got 16. And actually, so as Laura said, when they're anti-aligned, you don't get much contrast, but because our bars are slightly different heights to each other, we don't lose all contrast in the MFM in our thing. So as he also said, they are different heights precisely. So we had a width mod before, now we're doing a height mod instead, if you like, but again, that changes the coercivity a little bit. And so we can access any of the states that we want. And so here are some MFM pictures showing that we can access any of the states that we want, with the simulation showing what we expect them to look like. And then also here it is in an array. Okay, so firstly, can we make a kind of standard Magnonic crystal? And so just to look at some states and like how we can move the modes around. So if we set up a state so that essentially, well, if we make it so all the islands are parallel with each other, then the red curve here shows the FMR spectrum. And so you can see we've got one very dominant mode, which is at about 10.6 gigahertz. And then if we set the state so that every single vertical island pair is anti-parallel to each other, which is obviously where they want to be, then we get the blue curve here. And so here we've got a reconfigurable difference of about 1 gigahertz, which is certainly much bigger than we can generate it in the 2-dimensional system. So that's extremely nice. And so here's an MFM showing the thing, and you can see we can just about see all the contrast, but everything is super pale. And actually, so here you can see here's one particular defect where the top and bottom are parallel, and you can see we get an absolutely screaming MFM contrast in that one particular bar. Okay, so that's all very nice, but what about the kind of the non-linearities or the magnon-magnon coupling? Okay, so these are the sims done by Troy. And so what we're going to look at here is like what happens to the mode of the top bar and the mode of the bottom bar, or the modes, as we bring the 2 bars closer together. So over here on the left-hand side, so here we have a spacing of 250 nanometers. And it says no coupling. What that means is no magnon-magnon coupling. And so here you can see is that the green mode is the bottom bar, and that's anti-aligned with the field, so going down. And the purple mode is the top bar, which is aligned with the field, so that's going up. And you can see that there is a clean crossing, but not an anti-crossing. Okay, so they're not coupled to each other, so they just kind of go by each other without any hybridization. And now we're going to look at how the spectrum evolves as we bring the top and bottom layer closer and closer together. So if we put a spacer of 80 nanometers in, you can see I've called it weak coupling, but if you like, that's not ultra strong, perhaps it would be a better term. You can see we're already getting a gap emerging between the two things of the order of a couple of gigahertz. So at least compared to what we can achieve in 3D and people can achieve in most of the systems, this is like an enormous hybridization gap already. But then as we go closer and closer, we kind of cross over into what we've called the ultra-strong regime. So you can see these other modes appearing in the middle, and that's because these are modes which were previously at higher energy being pushed down or crossing over with our main modes. And so here are our main modes. We can see them evolve. And so you can see this gap gets bigger and bigger. And so down to a spacer of 20 nanometers, it's of the order of 6 gigahertz. And so that's absolutely enormous, at least compared to the frequencies we're at. So I think it's more. So basically, that's the simulations. Can we see these things in experiment? Okay, so here are our measurements of the heat maps. And so firstly, in the parallel state, you can see we just have the Kittel modes, and they're all parallel to each other. But if we put it in the anti-parallel state, you can see we've got this new mode that's come in here. And basically, this matches perfectly with the hybridization simulations. And so basically, at least where we are hybridized, then this is becoming an acoustic mode and an optical mode of the collective top and bottom layer together. Okay, and so at least there are various metrics for assessing how strong the coupling strength is. And so typically, you look at the size of the gap in frequency over the frequency of the higher mode. And so essentially, this metric is generally that ratio. And so above 0.1 is called ultra strong. In our 2D artificial spin ICs, we were closer to 0.01. But here we can measure this coupling strength coming up to 0.57. So really, really huge. Okay, and we can really prove that these are acoustic and optical modes, because if we do the time traces, we can see that the acoustic mode, the two things are evolving perfectly in phase with each other, and the optical mode, they're evolving perfectly out of phase with each other. Sorry, okay, so in the last 3 minutes, I'll just very quickly show you another nice thing that we've looked at, which is a Magnon frequency comb. And so optical frequency combs are hugely important in things like metrology and computing, and they let you introduce nonlinearities in this very specific way. And so the idea is that we can try and make a Magnon frequency comb. And essentially, there's a very nice PRL here, which suggested if you have a collinear film with a skyrmion on top, then you can get a chiral skyrmion. You can get this coupling from the breathing modes to the modes of the underlayer and achieve this combing. So we'd like to explore that in our system. So here are our macrospin modes. But as I said before, we can put a vortex in one of these things. So if we do that, what happens? And certainly, you can see in our measurements that we do start to see this kind of periodically spaced modes with a tooth spacing of about 550 megahertz. So the first thing to say is this on its own is categorically not proof of combing, okay? So the measurements that we can do are not quite the right measurements, but it looks very encouraging, so we can explore it in simulations. And so in simulations, we can do the right measurement. So here is a map looking at all the different possible input frequencies and then all the different possible power spectra at that input frequency. And so when you do a map like this, then essentially you can kind of see the things that you want to see. Right, so essentially the first thing to say about this is that, so in our data, we ramp up the input frequency sort of along the diagonal, but then basically our measurement is just essentially the sum of all the different frequencies. We just look at the total absorption. So we don't have this resolution, which we can in the simulations. So then the diagonal line is obviously kind of what you'd expect. But then the next thing to notice is if we look at this horizontal line down here, then at very low frequency, we basically always get activation at any input frequency. And then this input frequency is the gyrotropic mode, or the gyration of the vortex. at 550 megahertz. And so basically any frequency will activate that. And then if you look at slices around where the bulk mode is, for example, at 6.2 gigahertz is where our bulk mode is here, you can see that you get all these lines parallel to the main diagonal. And so these are all the combing teeth. And so this is showing frequency combing behavior, just how we'd like to see it. And very quickly, so basically if you can modulate your vortex gyration frequency, and then here we've done it with a small applied field, then you get a linear change in the frequency of your tooth spacing. So these are some different tooth spacings we've got just by modulating slightly the gyration frequency. Okay, so that's all very nice. So hopefully I've convinced you that we've developed these 3D or 2.5D nanomagnetic artificial spin ices, and that even in this really simple structure, we can look at some really rich and complex physics, which is very applicable for computation. And with that, I'll leave that up, and thank you all for listening. Cheers.